Hi everyone, thank you for coming to my CEDAR talk. My name is Lindsay, and today I'm going to be talking about a technique I'm developing to resolve irregularity spectra in the high-latitude ionosphere using advanced modular incoherent scatter radars. So before I get into anything too deep, I should first introduce what incoherent scatter radars are, or rather ISRs. These are simply just powerful radars that are able to measure ionospheric plasma parameters such as the ion temperature, the electron temperature, the plasma density, and the line of sight ion velocity. Over on the left here, we have one ISR. This is the Chattanooga Incoherent Scatter Radar. It has since been taken apart and disassembled, but you'll notice that this one had a steerable dish, a big giant dish. And what it could do with this is it could point in a variety of different directions and resolve plasma parameters in those different regions. And it could even perform azimuthal scans, as we see over here on the right. So this is an azimuthal scan, and this is plasma density as a function of latitude and altitude. These were taken in the midnight auroral zone. And what Kelly et al. In 1982 did was they took these observations and they took a cut at 350 kilometers. And then they took a fast Fourier transform of that to create what is called an irregularity spectrum, which is essentially all the structures that we see sorted with respect to spatial frequency. That's one way to think about it. But anyways, what they saw was this enhancement over here, which was indicative of active precipitation on the day side. But what's strange about this is, like I said, these are midnight observations. So from this, they were able to conclude that active precipitation on the day side could even impact night side auroral zone observations. And this was a very excellent study. However, it was performed back in 1982, and since then we've developed new techniques, we've created new incoherent scatter radar facilities, and so now we can look at more regions with more updated methods, essentially. So what I am doing is I'm coming back to the study and I'm improving upon it using new methods. One of the ways in which I am doing this is I'm using advanced modular incoherent scatter radars. So over here is just one example. This is Riser North, or the Resolute Bay Incoherent Scatter Radar North. There are three that are located in the high-latitude ionosphere. This is the field of view of Riser North at a variety of different altitudes. This is Riser C, which is the Resolute Bay Incoherent Scatter Radar Canada. And then over here is Pfizer, which is the Poker Flat Incoherent Scatter Radar. And if you look at the look directions that a given ISR can give you, you'll see something like this. This is just one experiment that's run. So instead of steering this to look in a variety of different directions, what they're actually doing is they're phasing these little antennas that you might be able to see on here. This is all just a panel of antennas. They're phasing them together in order to create these different look directions. And what's really powerful about this is that they're looking in a variety of directions nearly simultaneously. And the advantage of this over the Chattanooga Incoherent Scatter Radar is that scan that I showed you earlier took about 12 minutes. And we know that the ionosphere can change within that time. So the temporal resolution of advanced modular incoherent scatter radars is much better than a steerable dish, the Chattanooga ISR one. However, the Chattanooga Incoherent Scatter Radar arguably has a better spatial resolution, and this is why I'm going to say that. So here I have a hypothetical riser N experiment, and between 200 and 400 kilometers, we have a range resolution of approximately 24 kilometers along a given look direction. The look directions are shown in red. These orange squares here show hypothetical places that we could take measurements in a given experiment. This is all hypothetical. This isn't based on a specific experiment. But what we can see is that if we were to look at a specific altitude, or one specific altitude or a very narrow region, we actually don't have a lot of observations within that. In fact, even if we have some sort of structure that's sitting within this region, we maybe only have one measurement of it. And comparing this to the Chattanooga ISR, that one was able to perform an azimuthal scan where they had a 10-kilometer horizontal resolution, and we just don't have that in this case. However, we can cheat a little bit, and here's how we're going to cheat. We're going to recall that in the high-latitude ionosphere, we have a nearly vertical magnetic field. And we also know that between 200 kilometers and 400 kilometers, or more precisely within the F region ionosphere, the major transport mechanism parallel to magnetic field lines is diffusion. And so what that means is that if we have some measurement taken here or some measurement taken here, they should, along the same magnetic field line, infer some measurement that we have at another given altitude. In other words, these ones should be related. So even though we have some sort of Chapman profile that's occurring in the background, as I've indicated with the HMF2, there is some way that we should be able to infer these measurements. And through that, we can increase the spatial resolution at 350 kilometers. And so what I'm doing in this work is I'm finding a way to map or create some sort of multiplication factor to take this value from here and map it up from here, map it up to here, or this value at the HMF2 and decrease it to map to this value here. Another way that you can think about this is I'm trying to create a reliable profile of the plasma density background. So how I'm going to be doing this is in this presentation, actually, I'm not going to show any actual ISR observations. I'm only going to be showing you modeled ISR observations. So I'm going to be doing that with the International Reference Ionosphere, or IRI. I'm going to be taking plasma density measurements from that. So over here on the left, we see a very boring plasma density. So here on the x-axis, we have geographic longitude at a variety of degrees. Here we have the plasma density, and this is at 78.1 degrees latitude at 350 kilometers. I chose this region because it overlaps with riser north. And this blue curve here is just IRI observations. But what I'm taking and I'm putting on top of that is a plasma density enhancement. I'm just introducing a parabolic, very simple enhancement, which I'm going to say is a simplified polar cap patch. And it's elongated in latitude, but it varies with respect to longitude. And so then what I'm going to be doing is I'm looking at our IRI observations with my ISR, essentially. So I have all these positions that are measured in the imaging LP experiment mode by riser N. So this is a 52 beam mode that's performed by riser N reasonably frequently. And I'm taking all those positions and I'm measuring them with, I'm taking all those positions and I'm measuring IRI data with that. And then if I take all these points here and I just take a curve of that, or sorry, if I just plot them with respect to density and altitude, then I get a curve like this. And then if I introduce my plasma density enhancement, I see something like this. So here I have my enhancement that's elongated in latitude but varies with longitude. You'll notice that there's some variations from the beginning and the end of these look directions. And the reason why is that these are altitudinal variations. These are just the Chapman profile acting, which makes sense because this is just a model. But yeah, if I take all these points, then I can create this curve here, which are all the plasma density values in here. And so I've tried many different ways, many different mapping techniques to take my plasma density values that I measure at one altitude and mapping them up to 350 kilometers. In this presentation, I'm only really going to talk about two variations of those. But really, you can group all the different mapping techniques that I have tried and are possible to try in two categories. First, what you can do is you can use the fact that you know that your curve, your resulting plasma density profile should match the Chapman profile. And then take the Chapman profile and correct it with respect to your data to create this sort of background curve. Or what you can do is you can just use your observations to infer a background plasma density profile. And so over here what I have, so this is without my plasma density enhancement, without my patch really, and then this is with my patch. The red curve in here is if I take a Chapman profile and I correct it with respect to my data, and the yellow curve in here is if I just take a cubic spline to my data. And you'll notice that I have a cutoff of 220 kilometers because it seems like there's some sort of different plasma density regime that's acting here, so I don't want to include those in my fit. As well, I'm not going above 400 kilometers because I don't want to go above where ISR observations are known to be the most reliable. which is between 200 and 400 kilometers. Or if you're looking at the F region, that is, if you're using long pulse data, which I will be. And then over here is if I introduce some plasma density enhancement, and we see that between the red curve and the yellow curve, there are some variations. So in other words, there is a difference between introducing a Chapman profile and correcting it versus if I just take a cubic spline of everything. But what we can do is we can now use these different curves to map points that we have down here up to 350 kilometers. We now have a way to correct from this altitude up to another altitude. Oh, and I forgot to mention that I'm only fitting with the blue curves in the blue points in here. So the black ones are just providing context. So anyways, this is before I introduce a plasma density enhancement and artificial enhancement. These are just IRI values that are mapped up to 350 kilometers. So this is if I use a Chapman profile mapping, and this is if I use a cubic spline. And we see that there isn't a lot of variation within these as well. It's all quite boring, really. But what I can do is I can take my map values and I can subtract what I would expect to get at these given values. So they're all mapped to 350 kilometers. And I can take my IRI values at 350 kilometers and find the difference between that. And so we see that if we map these values to 350 kilometers and subtract the expected, we actually, both of our techniques are fairly accurate. And this yellow curve in here is just a cumulative distribution function reflecting like how the variety in our residuals essentially. So this is if I do incorporate a single enhancement and then I map those values at a variety of altitudes up to 350 kilometers. So this is a projection at 350 kilometers for that. And we see that there's quite a lot of uniformity in here. Like there is an enhancement in the middle, of course, but like it's all quite smooth. And this feature is quite extended in latitude and it's fairly clean. Same can be said for when we have a cubic spline. And then if I take these map values here and I subtract what we would expect to have at 350 kilometers, I'm very happy that actually our residuals are quite close to zero, which indicates that both of these mapping techniques are fairly accurate. And that in both cases, we're within like 0.5 E11 of what we would expect. But I can even play more complicated games. So this is just a funny example where I have two elongated features. They're elongated with respect to longitude this time. And I decided to put one of my polar cap patches, in a sense, on the fringe of my field of view. And even when I do that, both of my mapping techniques are fairly accurate. They're fairly localized at zero, which is excellent, which shows that both of these mapping techniques, whether or not we use the Chapman profile, are fairly accurate. But the real determining factor in which mapping technique is the most accurate is which one provides the most accurate spectra to what we would expect. So here I'm taking my density values that I've measured in these curves here, or in these my density values that are within these figures here. And I'm calculating spectra from those. So you'll notice as well, because I have an irregularly spaced number of density measurements, I can't take a fast Fourier transform of that, so I have to use a long Scargill periodogram. So these are the different spectra that I get. So this is the spectra that I would expect for when I do and don't have a polar cap patch sitting in here. This is the spectra that I get for when I do Chapman profile mapping to 350 kilometers. And this is if I do a cubic spline mapping up to 350 kilometers. And one thing I do appreciate is that we were expecting that all these should in some sense look like a sync function. And we are seeing that. We're seeing little variations in the tail. As well, one thing I do appreciate is that when we incorporate a single enhancement, we see that there is an increase on this end of the spectra for all these. And the reason why that makes sense is because these are sorted with respect to spatial frequency. So over here, these are smaller scale structures, and over here, these are larger scale structures. And so we're seeing an enhancement in the smaller scale structures, and that makes sense because we're introducing a patch. However, there are still features in here that we don't really understand, and some of these features undoubtedly are due to our field of view being restricted. But overall, one thing that I would also like to note is that these expected curves are the closest to the cubic spline mapping. So in conclusion, we're using AMISR observations and mapping techniques in order to be able to resolve high resolution plasma density measurements at one specific given altitude. We are developing newer techniques and new sophisticated mapping techniques. And what we found so far is that the spectra resulting from just a simple cubic spline mapping technique is the closest to what we would expect. However, there is a whole bunch of future work that we need to do. We need to fine tune our mapping techniques, test their limitations, and quantify their influence on the spectra. We need to examine plasma density depletions. Typically, when we talk about plasma structure, we usually just think of enhancements, but the depletions are also quite important. We need to characterize the spectral features that we see and determine which ones are a result of plasma density changes versus just funny fast Fourier transform math or Lomskargel math. It would also be great to introduce tapers into this. So a taper is just essentially a fancy way of cleaning up your spectra by using windowing. And up to this point, there hasn't been too much done on Lomskargel periodograms and tapers, but there was a paper earlier this year from Springford et al. 2020, which talks about how you can introduce tapers into Lomskargel. And of course, I've done on the side applied these techniques to real data, but it would be great to actually present what these mapping techniques do to real data. But yeah, that's all I have. Please feel free to get in contact with me through either formal channels like email or informal channels like Facebook. And thank you very much and enjoy the rest of your CEDAR.